These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm, or you can just use the link in the info box. Thank you. So, just an introduction to mass spectrometry?
We have not gone over it at all.
Okay.
So, yeah.
Well, shall we start?
Yeah.
Okay. Now, the purpose of spectrometry and spectroscopy is to provide clues about the structure of the molecule. We know that when we're looking in the chemistry textbooks, they just give us pictures of the molecule. But in lab, we don't see a picture in the test tube. We don't really know what the molecule is. We need some clues. So we have to see what are the types of clues we can get from mass spectrometry. Well, in mass spectrometry, we start with the original molecule. And we can call the original molecule capital M. So capital M stands for the original molecule. And then we hit that with a high energy electron. We hit the molecule with a high energy electron. And what the high energy electron does, roughly speaking, is it ricochets off the molecule and knocks another electron loose. This high energy electron is going to knock another electron loose from the molecule. So what should be the correct symbol for the molecule now? Well, now that the molecule has had one of its electrons knocked loose, it's a radical. We know that we draw radicals with unpaired electrons. And since it's lost an electron, it must have a positive charge. So the symbol we would use is to show that this is a radical cation. A radical cation. And then, and this is what we're going to call the molecular or the parent ion. Then we allow this molecular ion to go into the detection apparatus, and it will be detected. The apparatus, we're not going to go into the details, but the apparatus uses a magnetic field to detect the properties of what's going through the apparatus. We're going to use a magnetic field. Have you guys taken any physics? Yeah? So I don't know if you remember from physics, the magnetic force only affects charged particles. Magnetic force only affects charged particles. Do you remember the formula for magnetic force? QVB sine theta. It only affects particles with a charge. That was the whole point of making this into a cation, so that it'll be affected by the magnetic field in the detection apparatus. We need to give this a charge so that it can feel the magnetic force. Now what the apparatus can do is it can use adjustments of the magnetic field to determine the M/Z ratio. The apparatus can figure out the M/Z ratio, where M stands for mass and Z stands for charge. We're not going to have time to go through the details, but by adjusting the magnetic field, we can determine what the M/Z ratio is for the particles that go through the apparatus. But what is Z for this molecular ion? 1. It's only got one positive charge. So then the M/Z is just going to tell you the mass. And it turns out that almost all of the particles and fragments that we're going to run through the apparatus, they're all going to have charges of 1. So even though technically speaking, the apparatus tells you M/Z, in practical terms, it basically tells you the mass. Since all of the particles we're shooting through, almost all, will have a charge of 1, for all practical purposes, we can think of M/Z as just telling you the mass. We have to call it M/Z because that's what you'll see it referred to in the problems. It'll be called the M/Z ratio, but since Z is just going to be 1, it's really just the mass. It tells us what the mass is. So for example, and then this horizontal axis here tells us basically the mass of the particles that are detected. And the vertical axis is basically a measure of abundance, how many of the particles are making it to the detector. So for example, the molecular ion will give us a peak like this that shows how many of the molecular ions are getting to the detector. And then we can look at the horizontal axis to see what the total mass is here. So for example, suppose that the original molecule was methane. Well, if the original molecule is methane, then the molecular ion is the radical cation of methane, and then the m over z would be 12 plus 4, or 16. And you would get a mass here of 16. Okay. Now the complication here is that other particles besides the molecular ion are going to be detected because after you create the molecular ion, it can fragment further. The molecular ion can fall apart into fragments. For example, this molecular ion of methane here might lose 2 hydrogens. So then it would look like this. And this is also going to make it to the detector. This will also be detected, but this will be detected with a mass of 14.
How do you know the relative heights?
Well, in many cases, you can't predict them ahead of time. You just look at the piece of paper to see what the relative heights are.
Okay. So they wouldn't like have us draw a spectrum?
Probably not. They wouldn't make you draw the whole spectrum. Now, there are some cases when we can predict things about the relative height, so hopefully we'll have time to talk about that in a second. In some cases, we can make predictions about the relative heights, and in some cases, we can't. But in any case, if you look at the printout, you'll see what the relative heights are. So the way I've drawn this, I've drawn that there was more of the molecular ion reaching the detector, what was this, 12, 14, than of this fragment. And the way I know that is I just looked it up in the book, and the book said that there would be more of this than of this. There would be a whole bunch of other fragments too. So there's many different ways that this can fragment, and that's going to give us a whole bunch of different peaks. So we'll get a whole bunch of different fragmentation peaks, and there's various clues that we can get out of that. Now, in this particular case, I believe that for methane, this molecular peak really will so one thing to notice is that the molecular ion peak is always the furthest to the right, roughly speaking. You can see that the parent ion is always furthest to the right, roughly speaking, because obviously the parent ion is heavier than any of the fragments. Clearly the parent ion is heavier than any of the fragments, so roughly speaking, it has to be furthest to the right, and the fragments should be further to the left. So how can you find the parent ion? Well, pretty much you look at the farthest to the right peak. We'll see a complication maybe in a minute. But that doesn't mean that you have to have the greatest vertical height for the molecular ion. Sometimes the molecular ion does have the greatest vertical height, and sometimes it doesn't. Remember that the vertical height tells us what the abundance is of that particle. It tells us how many of those are reaching the detector. While sometimes the original parent ion is the ion that reaches the detector in the greatest abundance, but sometimes one of the fragments reaches the detector in greater abundance. I think for methane, the parent ion really is the most abundant. So maybe I'll erase the methane here. But there could be other situations where maybe this is the highest peak. That means that one of the fragments accumulates in more abundance than the parent ion over here. That means most of the parent ions are fragmenting. Well, this, remember, is called the parent. And this is called the base peak. the one that's highest vertically is the base peak, and the one that is furthest to the right is the molecular or parent peak.
Could the base peak be the molecular parent peak?
That's certainly possible. Remember that a second ago we were saying that that was the case for methane. It turns out that for methane, the molecular peak is the highest. But the point is that the molecular peak may or may not be the base peak. Sometimes it is and sometimes it isn't. Conceptually, those are two different things. In the picture I have on the board right now, the molecular peak is not the base peak. We don't want to confuse those two terms. Base peak is the highest vertically, and the molecular or parent peak is pretty much the one that's furthest to the right.